Hi, this is Tom Kelly from Full Stack Academy, and today we're going to talk about the hash table data structure. At this point, we're familiar with the concept of a contiguous array, that is, storing data in adjacent cells in memory. However, let's consider some of the problems that come from storing data this way. For example, say we set aside an array with 7 memory cells, 0 to 6, and we want to store some information there, like this string that says hello. We can go ahead and put it there, but if we want to find it later, we have to check one by one through the array to find the one that we want. Check here in 0x40, it's not there. 41, 42, 43, let's keep checking. There it is. Now, if you found that annoying, that's sort of what your computer thinks when going through all the cells in an array to find a value. It does it much faster than we would as humans, of course, but it's still this relatively laborious operation. Another problem is, what if our data looks like this? We could store it in a contiguous array and just remember that index 0 is the value of Doe, and index 1 is the value of Ray, and index 2 is the value of me. But how are we as humans supposed to remember that? Code written that way would be extremely prone to bugs and human error. It's important to remember that it's an extremely profound concern of ours in writing code. That's not just writing code that a machine can execute efficiently, but more so writing code that can be easily understood and maintained over time by humans. With that in mind, we might come up with some kind of abstract data type that behaves similar to the way that a dictionary works in real life. A dictionary is an abstract data type. It also goes by the name associative array, map, or symbol table. But I like the term dictionary because it helps me visualize what it actually does. It stores a list of key value pairs, just like a dictionary holds word definition pairs. Dictionaries have a couple of properties that make them interesting. Each key in the dictionary is going to be unique. For example, you could store multiple definitions for the same word, but you wouldn't have the same word twice. You can also modify and look up the values stored at those keys. And if we were to stop there, we would have something called a struct, a collection of key value pairs that never add new key value pairs. You could imagine this in JavaScript as being an object that you're not allowed to add new key value pairs to. However, this dictionary abstract data type also supports dynamic alteration, adding and removing keys. This makes dictionaries trickier than structs, but it also makes them more useful for certain tasks. So now that we know we want this behavior, let's think about how we might implement this with a data structure. The classic data structure for implementing the dictionary abstract data type is called a hash table. A hash table has two main ingredients. Our first ingredient is that we need a contiguous array that's going to hold the values stored in it. And the second ingredient is going to be a special kind of function called a hash function, whose job is to transform some string key into a numerical index in that array. Let's focus on that first ingredient. Here's a very simple hash function. It takes some string as input, adds up the sum of the character codes of each character in that string, and returns the remainder of dividing that number by 7. Though this is very simple, it does two things that hashing functions must do. First, it takes a string of some arbitrary length and transforms it into a smaller value within a specified range. No matter how long a string we put into this hash function, we will always get a number between 0 and 6 because we're always returning the remainder of division by the number 7. Second, it always returns the same output for the same input. It's completely deterministic. So no matter how many times we invoke this function for a given input, we will always get the same output. Note that real hashing functions are typically more complex than this. They have an excellent distribution of output and some other slightly more esoteric mathematical properties. We could spend an entire semester-long class talking about them if we wanted to. But let's not for now. What's important is that this hashing function, as simple as it is, does those two things that we care about. The second ingredient for our hash table is a contiguous array to store the values. So let's say that our process asks the operating system for some memory, and it gives us 7 contiguous memory cells starting at address 0x40. Now, the data we want to store is information about a person's contact information. For example, a person might have a name and a phone number. Remember, we could say, okay, I've got this array, I'm going to store the name in the 0th index and the phone number in the first index and so on and so forth. But that's difficult to remember. It's not very ergonomic from the developer's perspective. Instead, we'll associate each value with a key. So in this case, a contact's name, we might associate with the key name. And because this hash function always returns a number between 0 and 6, which corresponds to the indices of the array, we can put our key into the hash function and use its output, which will be a number between 0 and 6, to determine which memory cell or index should hold the value. Name, for example, might give us the value 5. So we'll store that the name at the memory address 0x40 plus 5. Then if we want to retrieve that value later, we don't have to search cell by cell for it. We just need to take the key, put it into the hashing function, and it'll tell us exactly where to look. It will give us the value 5, so we can perform that same mathematical operation 0x40 plus 5 to determine which memory cell to look into. Let's look at this contact info example in more depth. Here's our goal. We want to store the value Grace with the key name and the number value 8675309 with the key phone. So here, for example, say that we have a 9-bucket array. That is a hash table that is using a contiguous array that has 9 spaces, 9 indices, starting at 0 and going to 8. We want to store the value Grace for the key name. So let's say that hashing the string name with our hashing function yields the numerical index 3. This means that we'll store Grace at index 3. So now if we want to store the value 8675309 for the key phone, let's say that it hashes to the value of 7. So we'll store 8675309 at index 7. Then later on, when we want to fetch these values, we might hash the string name again, which will yield, once again, the numerical index 3. And then we'll find the value at index 3, which is going to be the string Grace. And we'll follow similar steps when retrieving the value for the key phone. So pause the video here and take a moment to think. Is there a problem with this system? The problem is, what if two keys hash to the same index? This is called a collision. Say, for example, we now want to store our contact's email. So say we have the value grace@gmail.com for the key email. Let's say that we hash the string email, and that also yields the numerical index 7. But we already have a value there for phone. And this is because there are many more possible keys than there are buckets in our array. So a collision with a contiguous array of this size is inevitable. To be fair, we're using a very exaggeratedly small number of buckets in this example. A good hash table is going to have a lot more buckets, which reduces the odds of a collision. And for rather esoteric reasons related to the hash function chosen, a prime number of buckets typically results in better distribution of values, that is, fewer collisions. But even with a decent number of buckets, it's still going to be very limited compared to the gargantuan number of possible key strings. And note that if all permitted keys are known beforehand and enough buckets are provided, it is possible to have a perfect hash function which maps each key to a unique bucket, but that's not typically going to be our case. Take a moment and pause the video again. How can we resolve a collision? There's more than one answer. There are two main strategies that we could take. The first strategy, open addressing, says that if a bucket is full, we'll go ahead and find the next empty bucket and place the value in that spot instead of the original. The second approach is called separate chaining. With separate chaining, every bucket stores a secondary data structure, like a linked list. So that way, collisions will instead create new entries in that data structure. The exercise that you're about to do will take the approach of separate chaining because it tends to be easier to implement. Here's how separate chaining works. Instead of just storing a value in each bucket, we actually store a linked list, which will hold the values. So let's go back and say that we have our value grace@gmail.com for the key email. We hash the string email, which yields the numerical index 7, but that bucket already contains an initial list node with the value 8675309. So what we do is we add this value to the linked list as a new node. We still have a problem though. Pause the video again and see if you can spot it. The problem appears when we try to retrieve a value. How do we know which value we want for a given key? So say that we've stored grace@gmail.com as a second list node in the linked list at index 7. When we try to retrieve it later, we'll hash the string email, which will yield the numerical index of 7. We go into bucket 7 and see that there's a linked list there, and there are two nodes in that list. But how do we know which one is the value for the key email? Is it 8675309, or is it grace@gmail.com? Try to think for a moment about how you might solve this. One possible solution is that we could store both the key and the value. So let's see what this looks like. So we'll hash email, which will yield the index 7, and in bucket 7 we'll see that there is a linked list. So the head has a key of phone, so we know that that's not our key email, so we'll keep looking. And then the next node has a key of email, so we'll be able to return the value, grace@gmail.com. So if we end up storing our data in the hash table within a linked list, then how exactly is a hash table better than a linked list? The answer is that ultimately a hash table is going to be much more performant. Our example used a small number of buckets and had a very basic hash function, but hash tables in real life typically have many buckets and use a good hash function that will be unlikely to produce collisions. Usually, assigning or checking a key value pair just takes one step, invoking the hash function to find the index that you need to go to. And though sometimes collisions occur, you'll only be traversing a few linked list nodes rather than all the data that you've stored. Let's return our attention to this concept of having list nodes that store key value pairs. You might have taken this for granted, but remember that the list nodes you implemented in class could only contain value and next. Let's take a moment and pretend that we're working at a much lower level where we might have to take this decision pretty seriously. Let's consider a few solutions. One solution is we could use a variant of a linked list called an association list. Association lists are linked lists that don't just store a value, but instead store key value pairs, which makes them ideal for using in hash table buckets. You'll actually end up building one of these during the exercise, but consider that the downside here is that you need to build a brand new data structure. You can't just reuse the linked list you already built. So what if we wanted to reuse that existing linked list? We would need to figure out how to store multiple elements in the value field of the list node. One approach we could take would be to wrap them in a container like a contiguous array. The downside is that storing the hash table key in index 0 and the hash table value in index 1 is pretty opaque. It has that same ergonomics problem that we've seen before. Slightly better would be if we could use a struct, which is another way to store properties with string keys. This might seem like cheating, but remember that with a struct, you have to predefine all the keys that it can never have. It can never have new keys added or removed. JavaScript doesn't have structs, but if we were implementing this in JavaScript, we could pretend that a simple object is a struct, so long as you never add new keys, that is, new properties to it. Speaking of JavaScript, though, a lot of what we've been imagining when we're modeling this data structure is that we're dealing with a lower level language like C. So let's take a moment to talk about how this pertains to JavaScript, a much higher level language. Hash tables, of course, sound just like JavaScript objects. However, you might be surprised to learn that most JavaScript engines, like Google's V8, actually don't use hash tables for most objects. They use something like an immutable list of structs. This might sound a bit crazy, but because the V8 engine knows how to reuse these structs, which actually results in less memory usage most of the time. We'll revisit this concept later in the course when we talk about functional programming and immutable data structures. However, if the engine does see that your object is so big that using linked structs would actually be wasteful, then it will optimize by switching to use a hash table. In the end, the moral of the story is that the object that's specified by ECMAScript is just a data type. We know what kind of behavior it should exhibit, but not necessarily how it's implemented at runtime. That's ultimately going to be the decision of the JavaScript engine.